Hello everyone. In this session, we are going to discuss relations and functions, and which is the third module of discrete mathematics. Okay, so these two terms, relations and functions, I'm sure that you must have seen this in lower classes, like in your ninth grade or 10th grade. You must have seen these two terms, relations and functions. And in this module, again, we are going to discuss this term in detail. Okay, especially we are going to discuss this one with certain applications of computer science. So first let's go to the definition of these two things, relations and functions. All right, so before we start, uh, this is what the first term, Cartesian product. So we start from Cartesian product. All right, so let A and B be two set. Okay, uh, let A and B be two sets. Okay, sets in the sense, A and B contains numbers. It can be integers, it can be real numbers, it can be complex numbers, whatever, right? So A and B be two sets, and the number of elements in A and B that may be finite or may be infinite. That depends on the different cases. Okay. So we have two sets A and B, and we define the Cartesian product of product of A and B, which is denoted by A cross B, and is defined as which is defined as A cross B is equal to set of all ordered pairs A and B, where A belongs to A and B belongs to B. This is what the classical definition of a Cartesian product. That means A cross B is a Cartesian product of A and B. So it's again a set. That set contains coordinates A, B, where the first coordinates are the elements from A, and the second coordinates are the elements from B. Okay, so we have to take all such combinations. Okay, all such combinations A and B. Okay, so this is called the Cartesian product of A and B. And let's see an example. So if let A is equal to set 1 2, and B is equal to some ABC, then we define A cross B as set of all. See, we can express that something like this. See, this is 1 2, and this be A, B, and C. All right. So these are the possibilities. If I take the first element as 1, still we have three other options in B. That means 1A is one choice, 1B is another choice, and 1C is another choice. So these are the first three elements. All right. So we can write that as 1A is one element, then 1B is the other element, and 1C is the third element. Not only that, we can consider the other element 2 also. So with regard to 2, there exists an element A in B, and then 2B and 2C. So these are the other three combinations. So this is the set A and this is B. Okay, so the other elements are 2A, okay, 2A, and then 2B, and then 2C. All right. So these are the elements of A cross B, or the Cartesian product of A and B. And we can see that it contains total 6 elements, right? That means we need to use the uh, fundamental principle of counting here. So A contains 2 elements and B contains 3 elements. So the total number of elements in A cross B is the product of number of elements in A and number of elements in B. Alright. So the number of elements in A, so we denote A cross B. This is the this one represents the number of elements in A cross B. Okay. So we can write this as the number of elements in A cross B. A cross B. And to find the number of elements in A cross B, it's enough to find the number of elements in A and multiply that with number of elements in B. Okay, so this is what you will get. So in the previous example, so in the example, you know, Cartesian, the number of elements in A cross B is number of elements in A was 2 and number of elements in B was 3. So total there were 6 elements, right? 1, 2, 3, 4, 5, 6. So total there are 6 elements. So these are the Cartesian product of two sets. Okay, and this idea can be extended. Okay, that means if A, B, and C are three sets okay, then we can define A cross B cross C. A cross B cross C also can be defined. So A cross B cross C, and this one contains a triplet A B C, where the first coordinate A is taken from A, and the second element B is an element of set B, and C is taken from the set C. Okay, so this is what the definition, and in general we can extend this one to n different sets. That means A1 cross A2 cross etc cross A. So we can define the Cartesian product of n sets. Okay, so this is what the basic idea. All right. So I'll just mention some of the examples like. So we have seen a particular example by taking A is equal to 1, 2 and B is equal to A, B, C, and we have seen what is A cross B, right? That is what we have seen. And here, note that both A and B are finite sets. A contains only 2 elements and B contains only 3 elements. Okay, so that need not be the case always. For example, you can take, n cross n, and what is this? N is a set of all natural numbers. Okay, so that means we know that n is equal to like 1, 2, 3 up to infinity. All right, this is n. So what is n cross n? So n cross n will give you again some combination like this, m comma n, where m and n both belongs to n, and this is what n cross n. Okay, and this one contains infinitely many elements, right? Because n contains infinitely many elements, and this n also contains infinitely many elements. So definitely n cross n contains infinitely many elements. So if one of the set is infinite, then uh, definitely the cross product also will be containing infinitely many elements. All right. Okay. Now let's move on to relations. What is the definition of a relation? All right. Let's see what is a relation. Okay. So this is what we are going to define. A relation, a relation from A to B. A relation from A to B. This is what we need to define. Okay, so A and B are two sets. Okay, so uh, a relation, this is what the definition, a relation from A to B is the subset. Okay, a relation from A to B is the subset of A cross B. All right, that means we know what is A cross B. We have just seen what is A cross B. So any of the subsets of A cross B is called a relation from A to B. All right, so that is what the definition of a relation. Okay, let's see an example. In the previous example itself, we have seen see, A is equal to 1 2, and we have taken B is equal to ABC, right? And A cross B is the set of all 6 elements like 1A, 1B, 1C, and 2A, 2B, and 2C. So these are the elements in A cross B. So if you choose any subsets of A cross B, that becomes a relation. So let me call the first relation as R1. R1 is a relation. So that becomes any of the subset. For example, if I choose only one element from A cross B, right, 1A, and this is the relation. This is the relation from A and B. Alright, from A to B. Okay. So if I choose another one, it's like set of all 1A, 1B, and 1C. This is another relation. Okay, or you can choose another relation as R3, and that is just A cross B itself. That means every set is a subset of itself. So I can take R3 as A cross B itself, and that itself is a relation. Okay, and okay, I'll show you one more, and that is the null set. The null set is always a subset of any set. So as per definition, it's again a subset, right? So that becomes a relation from A to B. Okay, so these are the so you can choose any subsets of A cross B that becomes a relation, right? So now the question is, how many such relations can be possible? How many such relations can be possible, right? So okay, when you think about that, you can see that uh, how many subsets how many subsets are possible for a set. Okay, that many relations are also possible, right? Because every subset is a relation. So the number of subsets of A cross B will give you the number of relations. Now the question is, how can we find it out? Okay, so this is the next question. What is the number of relations from A to B? Number of relations from A to B. Okay, and provided assume that both A and B are finite. Alright, both A and B are finite. If any one of this one is not finite, then what happens is that that A cross B will be containing infinitely many elements. So the number of subsets will again be infinitely many elements. So okay, so so the number of relations from A to B is equal to, we can write that as a number. So it is the same as the number of subsets of A cross B. Okay, so for a set, the number of subsets is always 2 to the power cardinality of that set. Okay, and here the cardinality is A cross B, so 2 to the power cardinality of A cross B, and that means cardinality of A cross B is nothing but cardinality of A times cardinality of B, right? And if I denote cardinality of A is equal to M and cardinality of B is equal to N, then this is going to be 2 to the power Mn, where A contains M elements and B contains N elements. So total 2 to the power Mn relations are possible from a set of M elements to a set of N elements. Okay. All right. Okay. So this is all about relation. And now let's see what functions are. Functions are nothing but relations. Okay. Function is also defined from A to B. This is how we denote. So f is a function from A to B. All right. So this is the definition. A function is nothing but a relation. a relation from A to B. All right, a function is a relation from A to B such that this is what the characterization of a function. Okay, uh, every element of A has a unique element, not an element, a unique image in B. Every element of A has a unique uh, image image in B. Okay, so such a relation is called a function. Okay, for example, as in the previous case, I think to understand a function, it is always better to draw some figures. All right, so uh, okay, so I'll show you this one by taking an example. Let's consider the previous example itself. So yeah, so I'm taking A as set 1 2 and B as set ABC. All right, I need to find a function from A to B. Right, I need to find a function f from A to B. Okay, so this is how it looks like. This is A and this is B. I need to find a function from A to B. See, there are many functions exist. Okay, but how can we write one? So this is the set A and B contains elements A, B, C. Now let's see how can we map. How can we map 1 and 2 to B? Okay, so that it becomes a function. F becomes a function. Okay, so this is the definition. Every element of A has a unique image in B. So that means one should have an image in B and two also should have an image in B. Okay, so one is mapped to A. Okay, so I can map any one of this one, but initially I choose one is mapped to A. Right, okay, now 2 also should have an image, right? So I take 2 also to be mapped to A. So 1 is mapped to A and 2 is mapped to A. And check these two conditions are satisfied. Yes, every element has an image. So 1 has an image A and 2 has an image. And that is alright. So the first condition is satisfied. Now let's see the unique image. Every element has a unique image. Yeah, one has only one image, right? One has only one image A and 2 also has one image A. Okay, so if one has two images, like if one is mapped to A at the same time, if is one is mapped to something like this, if one is mapped to A at the same time one is mapped to B, then this would not have been a function, because one has two images, right? It's not unique. Okay, so if it was so, it would not have been a function, but now it is, because one is mapped only onto one point A and 2 is also mapped only to A. So this is a function. All right, so from the definition we can say that this one is a function. So this is a function. This is a function. All right, or we can write see f is a function, and we can write f as a set, like 1a and 2a, and this is a function. See, this one is a relation, right? This one is a relation but satisfying certain condition, so this is a function. All right, now see what are the different cases where a relation is not a function. Okay, I'll show you that also by taking one example. Let this be the same set A and this be B. All right, and here I have 1 and 2 and here I have A, B and C. So F is a relation from A to B. Okay, so if I map 1 to A, 1 to A, and 1 to B, and 2 to C. This is not a function. This is not a function. The reason is that 1 has two images, right? So this is not a function because 1 has two images. That means the image is not unique, right? So one of the condition is violated, so this one will not be a function. All right, so this is one example, and okay, I'll show you one more example, like F from A to B. Again, I'm going to take the same set 1 2 here, and B is A, B, and C. All right, so see, if I map only 2 to B, right, 2 is mapped to B. That's it. I'm not going to give any mapping of 1, right? So we can say that this is not a function then. This is again not a function. You know the reason? The reason is that 1 does not have an image, right? 1 does not have an image. Okay, so if any relation like with these situations, definitely we can say that those are not functions. Okay, so the definition of function is, every element of A must have an image in B, and every element should have a unique image in B. Then it becomes a function. All right. Now, what is the domain of a function? Okay, so again, I'll write three definitions. First one, what is the domain of a function? Domain of a function. Okay. Then, what is the codomain of a function? And what is the range of a function? Okay, and assume that in all these cases, okay, so let this be the case, f be a function from A to B. This is what the general idea that we have. F is a function from A to B. Then what is the domain of the function? And here I can say that the domain of the function is nothing but A here, because the function is a mapping from A to B. Okay, so all elements of A should have an image, right? So the domain is nothing but this A. All right, and codomain from which set to which, to which set that function is defined. That to set is the codomain, and here it is B, right? Here it is B. Okay, now what is the range of the function? Range of the function is, when I take the images, we need to take all the images of the set B. Okay, images of A in B. Okay, and we write that as a function, like this is how we write it. It is the set of all f of A where A belongs to A, and this one will definitely be a subspace of B, and this is called the range of the function. All right. Okay, again, I'll show you an example. I define a function f from A to B, and this is what I have: 1 2, and B is going to be 1 2 3. And this is what the function 1 and 2 are mapped to 2. Okay, both 1 and 2 are having an image, and both will be having a unique image. All right, so this one is a function, right? And the domain, what is the domain here? The domain is nothing but A, and codomain, there is no doubt, codomain is B. And what is the range? Range is nothing but f of 1 and f of 2, right? That means the images of all these points. But here, see, in fact, f of 1 and f of 2 are same here, right? So we have only one element in the image set, so that is the range set. Okay, so here the range set is only 2. Okay, but the codomain contains these two elements also, 1 and 3, but the range set contains only 2. That means the range set always will be the images of the element of A. All right, so that is what the definition of the range. Okay, now I'll show you some standard examples of functions. Okay, some standard examples. Standard examples. First one, see, a lot of examples are there because sin x, cos x, all the functions which you have seen, like e to the power x, polynomial functions, exponential functions, logarithmic functions, all those are functions in its domain. Okay, in its standard domain. All right, so apart from that, so standard examples in the sense, I will just write it like sin x uh, and cos x. Okay, e to the power x, polynomials, all right, all these are functions from set of all real line R to R. See, these are the functions defined on R, set of all real numbers. Okay, so uh, we can draw that continuously, right? For example, this is what the sine function, right? This is what the sin x function, all right. See, every point on R, this is a real line, right? Every point R has an image, and that image is unique also. Okay, so uh, I've just drawn only one example, just sin x. So these are the standard classical functions that we use. All these are functions. Okay, right. Now I'll show you another one, and that is nothing but the greatest integer function. Greatest integer function, and this is a function which is used in computer science, definitely. Okay, so this is how we define. So it's a function. uh, this is how we denote it actually. So integer part, this is what it is, x. This is what the notation of that. It's a function from R on to R. All right, such that this is what the definition: greatest integer function or floor function. The floor function. So the greatest integer of x is nothing but the greatest integer, the greatest integer less than or equal to x. Okay, so we are supposed to calculate the integer which is less than x, less than or equal to x, but that should be the greatest integer, greatest such integer. All right, so that is what it is. For example, what is integer part of, I mean, a greatest integer function or floor function of 1.5, right? That is just 1, because just before 1.5 we have the first integer as 1. All right, so the integer 0.025, and that's 0, right? And the greatest integer function of point negative zero point 0.5, negative zero point 0.5, uh, just mm, keep in mind the real line. Okay, so negative zero point 0.5, so the integer just less than that is going to be negative 1. Okay, so the greatest integer function of negative 2.3 is going to be negative 3. Okay, so this is how it looks like. So this is called a greatest integer function. See, we can draw the graph of that also, like uh, I'll show you just one. So this is 0, 1, 2, and this is -1, and so on. Okay, if you take any number between 0 and 1, right? If you take any number between 0 and 1, you that is mapped to 0. that is mapped to 0. All right, but if you get 1, it's mapped to 1. Okay, and from 1 to 2 always it will be 1, but at 2 it takes 2. Okay, 2 to 3 it's something like this. All right, see, it goes like that. It's a kind of step function. Okay, it's a kind of step function. So this is what the greatest integer function. All right, next, all polynomial functions are definitely functions. Okay, and I'll introduce you one more function, and that is also applicable in computer science students. And here we go. I'm going to define a function. Hmm, okay, let me call that as some eta, okay, from n, set of all integers, to n, okay, such that this is how I define it. I take a positive integer and I define this as eta of n is the number of positive devices of n. Okay, for example, if I write eta of 6, how many devices of 6, how many devices are there for 6? You know, 1 is a divisor because 1 divides 6, 2 is a divisor, 3 is a divisor, and 6 is a divisor, right? So all these four numbers are the divisors of 6, right? So we can say that total 4. So mu of 6 is going to be 4. Okay, and what is mu of 4? 1 is a divisor of 4, and 2 is a divisor of 4, and 4 is a divisor of 4. So totally you will get 3. So mu of 4 is going to be 3. All right. So this is what the definition. Now, if it's a very small number, you know, it's really easy to calculate, you know, how many number of positive devices are there. As in the case of 4 and 6, we know what are the devices. So we just list it and we just count it and write it, right? But that may not always be possible for big numbers. Okay, so there is a formula to find the number of positive devices of n, and this is the formula uh, by by fundamental theorem of arithmetic. By fundamental theorem of arithmetic, okay, any integer n can be written as some p1 to the power n1 times p2 to the power n2, etc., some pr to the power nr. Any number, any integer can be written something like this, right? Okay, so for example, if n is equal to 12, 12 can be written as 2 square times 3 to the power 1, and here 2 is a prime and 3 is a prime. Okay, so it's looked like this, right? So any number can be factored something like this, and that is called the fundamental theorem of arithmetic. All right. Okay, once you factor like this, now what is eta of n? Now eta of n is going to be, just look at the powers here. You know, these are the powers, right? N1, N2, and Nr. All right. Just add 1 to all these powers and then multiply it, and that is what the formula for that. So this is what you will get: N1 plus 1 times N2 plus 1 times etc. times Nr plus 1, because there are only R powers here, right? These are the powers N1, N2, etc. Nr. All right. So this is what the formula for eta n. Or you can write that using a product form here. So product I is equal to 1 to r ni plus 1. We can write like this. Okay, so this is again a function, right? And this function is called the number of positive devices of n. Okay, and that's it for today's session. In the next session, we'll be focusing on the properties of relations and functions and problems based on that. All right, so let's wind up the session. Okay, thank you.